Thanks, Pinar. Hi, I'm Badrish Chandramouli from Microsoft Research in Redmond. And this is joint work with my intern, Gunaprasad from University of Washington, and my other colleagues at Microsoft, including Donald, Justin, Mike, and James. This work is on FASTR, which is a concurrent key-value store with in-place updates. So as introduction, we are witnessing a huge growth in data-intensive applications in the cloud, particularly in kind of these applications and services that receive a lot of data and have to maintain a lot of state. For instance, in an Internet of Things kind of setting, you have millions and billions of devices basically sending data to the cloud, where you maintain a large amount of information and update information, for example, on a per device or a per user basis. Other similar applications include things like data center monitoring, where you're measuring telemetry for example, in Azure. Things like streaming, online services, MapReduce, and all of these systems where you have to maintain a lot of state. So as expected, state management is a very hard problem in all of these kind of applications. However, these applications have some common characteristics, where the state consists of a large number of largely independent objects. For example, you have devices, users, ads, and so on, for each of which you maintain some amount of state. The overall state is typically very large and doesn't fit in memory of a small set of machines on which you want to kind of process this workload. The other characteristic is that point operations are usually sufficient. For example, you might want to do point reads and point writes. Further, there is significant update traffic. For example, you may want to very frequently update the per device or kind of the average CPU reading for each device. And this involves this atomic read, modify, write kind of operation. A common property across many of these applications is this notion of temporal locality. And I'll describe this with the help of an example. So, for example, in a large search engine such as Bing, you typically on the server side, you maintain per user or per ad statistics over the last week of data, for example. So the number of distinct users over 1 week could be a lot. For example, there could be billions of users. However, at any given instant, there's only probably a few millions of users who are actively surfing and making changes, right? So this is the notion of temporal locality, where the sessions start, do a lot of updates, and then basically expire in terms of value. So let's try to distill out some requirements from all of these applications. So you want to be able to support larger than memory data because the overall amount of state that you index is large. You want very high throughput for the working set because the working set happens to be much smaller, and typically you want to be able to support high throughputs. You want to optimize for heavy updates, and in particular this notion of atomic read, modify, write operations. Handle the drifting hot working set over time. And finally, you want to be able to, of course, recover after failure. However, if you look at today's basic broad classes of systems that try to address, that are used kind of to address these problems, none of them satisfy all these properties. The most common use in, for example, stream processing systems, including the Trill system that I worked on previously, is that they're purely in-memory, and they use in-memory structures like hash maps. And while they're extremely good for high throughput and optimized for heavy updates, they don't support larger than memory data and are not able to recover after failure. So you have to have additional characteristics to support that. Persistent key-value stores are often used in many large-scale deployments, for example, RocksDB. However, they typically target a much richer kind of workload. For example, they target range queries, and they do have persistence, but the throughput usually is less than 1 million operations per second, which is really not of the scale that we would like to target. Caching systems do support a drifting working set, and kind of they have this caching, but they do depend on some kind of key-value store or persistent backend, so they don't, again, satisfy our requirements. So what is FASTR? FASTR is a latch-free concurrent multi-core hash key-value store. It's an embedded component like Trill. And the idea of FASTR is that you can embed it into your application and get very high performance and scalability across all the threads in your application on a shared memory system. It supports data larger than main memory with recovery, and automatically shapes the hot working set that sits in memory without any fine-grained caching statistics. To give you an idea of performance, we support up to 160 million operations per second on a single machine for several YCSB variants that we evaluated. This was on a single machine with 2 sockets and 56 threads, where the working set happened to fit in memory for the workload. This, in fact, exceeds the throughput of pure in-memory systems as well. The FASTR interface, interestingly, apart from the traditional read and blind updates that are supported by many of existing systems, it supports the atomic read, modify, write, or RMW for short, which is super important in these kinds of workloads, particularly if you're maintaining running aggregates. or partial field updates. For example, if you have large field and threads are updating different fields in parallel. Faster is implemented as an embedded C# component using dynamic code generation, and that part I won't talk about in this talk. You can refer to the paper for details. The high-level system architecture is as follows. There's a set of threads that are feeding into the system. The system itself is composed into two parts. One is a hash index, which basically maintains pointers to records, which are handled by a separate allocator. The allocator can be either an in-memory allocator or two kinds of allocators, an append-only and a hybrid, which we'll talk about in the rest of the talk. The three key technical contributions of Faster are the threading model, where we extended the basic epoch protection framework that is popular in multi-threaded systems with the notion of trigger actions. For indexing, we proposed a new concurrent latch-free hash index that supports, it's very cache-friendly and supports very high throughput. And finally, the record storage, which in terms of a hybrid log record allocator, which I'll cover later in the talk. Let's briefly go through basics of epoch prediction. It's an old technique, and in the context of Faster, the system requirement was that we wanted to avoid any coordination between threads in the common case, in these short bursts of activity, where you can do some operations while not worrying about any other threads or memory safety. At the same time, you want to agree for the system on the mechanism to synchronize on shared system state. The best way to demonstrate it is with an example. We have 4 threads shown on the figure below as kind of as horizontal bars. The system maintains a shared counter E, which is the current epoch, and this epoch can be bumped by any thread. For example, the current epoch might go from 2, 3, 4, 5 in this example. Each thread keeps a stale local epoch counter that is copied over from E. And we have the notion of safety, where an epoch C is safe if all thread local epochs are greater than C. In this case, the safe epoch 1, epoch 1 turns safe at the moment thread 3 basically leaves epoch 1. So the notion of epoch protection is not new. It has been used in many systems in the past. Our modification to it is the notion of adding trigger actions. So what is a trigger action? The basic idea of a trigger is that we associate a function callback with an epoch bump from C to C+1. The idea is that the trigger action will be executed later on when C becomes safe. With this simple primitive, it turns out that you can simplify lazy synchronization in a multi-threaded system, and we'll use it in multiple places throughout the Faster system. So for example, let's say we wanted to invoke a function f when a shared status becomes active. The thread essentially updates the shared status to active. Of course, we don't know that all other threads have seen it. Then we bump the current epoch with a trigger that says invoke function f. Then you're guaranteed that all the threads have seen the active state before f is invoked. We use epochs plus trigger actions extensively. For example, for memory safety, non-blocking index resizing, log buffer maintenance, recovery. And particularly, the idea is that threads agree to respect the global system state at these epoch refresh boundaries. I won't talk about the hash index in brief, although there's a lot of interesting technical details there in the paper. But very high level, there's an array of hash buckets, and the bucket entries point to a linked list of colliding records, as shown in the figure. Note that keys are not stored as part of the index, but they are part of the records. And this allows us to keep the in-memory footprint that is required quite low. All operations are latch-free. The paper has interesting technical details on a new latch-free insertion technique in this case without having any bucket-level logs. It requires a two-phase kind of operation to pull that off. And of course, the index resizing, as I mentioned earlier, using epochs with triggers. However, in this talk, I'll focus on the record allocator, which has certain interesting characteristics. Let's start as a straw man with a log structure record allocator, which is what many systems that support larger than memory data use. The basic idea here is that you can create a single global logical address space starting from 0 to all the way to infinity, which spans both storage and main memory. So storage is in the upper part and main memory is in the lower part. The tail pages are in a circular in-memory buffer. All threads allocate at the tail with an atomic fetch and add, which results in a temporal log of records, right? Interestingly, you can use epochs with triggers even in this setting to ensure flush safety without pinning pages. The idea is that when a particular thread goes and does a fetch and add and reaches a new page, it can simply bump the epoch with a trigger action to flush the page. And we know that when the trigger action is executed, all other concurrent threads have finished writing to the previous page, so you can avoid pinning altogether. Unfortunately, just taking the Faster index with the pure log structure was not scalable. So here is an example of throughput versus number of threads, and we found that we kind of maxed out at around 10 million to 15 million operations per second, which is great for range indices, but for a hash index, you know that you can easily achieve hundreds of millions of operations per second. So this was not really good enough for us. And the reasons being that there's a heavy contention on the tail of the log. Every update is a copy on write, and log growth can tremendously stress your storage. So we defined a new allocator called a hybrid log allocator. The basic idea is that memory is divided into three regions. The first region is the stable region, which is on disk, which is basically uses read, copy, update. On the other extreme, we have the mutable region of the log, which is basically in memory, and it uses in-place updates for high performance. And in between, also in main memory, is a read-only region where we use read, copy, update. And the basic idea here is that a record that's in the read-only region gets a second chance to get copied back using read, copy, update to the tail so that it captures the temporal locality of the workload. Note that we have a hybrid concurrency model here where the read, copy, update involves a compare and swap on the hash index for concurrency, whereas for the in-place updates uses record level concurrency, similar to mass-tree, which is a pure in-memory structure. Now the tail grows, the offsets grow as well. So basically the regions of memory are constantly shifting over time as the tail of the log grows. Note that the new and updated records stay in the mutable region for a while, which again captures the temporal locality. So the basic read modify write algorithm is exactly what I said. Based on the region that you're in, you'll either issue an async IO request, or you copy to the tail and cast update the hash index, or you do an update in place. This removes the earlier bottleneck, and we get pretty much linear scalability all the way up to around 150 million, 160 million operations per second, which is great. This is an elegant design, but it was very hard to maintain multi-threaded correctness, and I'll talk about that in the next slide with one example. So note that threads are guaranteed to read the new offset variables only at epoch boundaries, because everything is lazy in our system and we don't want to take a lock on these offsets. So basically we need to be able to modify these regions of memory without having to take any locks on what memory is read-only and what memory is mutable. So this is a problem in the multi-threaded setting, because mutability for one thread might appear to be read-only for another thread. And as a very simple example, consider the problem of the read-only offset moving downwards. A thread 1 might see that the read-only offset in this case is R1, and therefore it sees a record and decides that it can do an in-place update. On the other side, a thread 2 might see a read-only offset of R2 and think that it cannot make an update, so it does a read-copy update. And then this results in the loss of the update by thread 1. Interestingly, the solution is fairly straightforward by introducing the notion of a fuzzy region. A fuzzy region is a region of memory whose mutability status has not been agreed upon by all threads in the system. And we track this using what we call as a safe read-only offset, which tracks the read-only offset that has been seen by all threads. Interestingly, it's again epoch protection with trigger actions to the rescue. So the idea is that when you move the read-only marker forward, you can bump the current epoch and set a trigger action. So that safe read-only offset is that value, and you are guaranteed that the safe read-only offset, when set, corresponds to a state that has been seen by all threads. So with a minor update to the read modify write algorithm, we have to make sure that if we are operating in the fuzzy region, you cannot really do a read copy update. Rather, you have to go pending. This is very similar to an IO, so that you can repeat the operation later when the region is no longer fuzzy. There are lots of other details in the paper that I'll highlight for time reasons, including the caching behavior, which is very nice because it avoids any fine-grained caching statistics. And there are other properties that we talk about in the paper. However, I'll very quickly go into the evaluation before concluding. We used a machine, a single machine with 56 hyperthreads, that is 2 sockets with 14 cores per socket, and 256 GB RAM with a fast SSD. We modified the YCSB-A workload to include read, modify, write, or RMW operations as well. 250 million distinct 8-byte keys with 8 and 100-byte payloads, and varying the fraction of reads and updates. R:U in our experiments indicates the percentage of reads and updates. The baseline systems were in-memory structures, which of course cannot handle larger than memory data, so it's not exactly an apples-to-apples comparison. We compared with the Intel TBB hash map and mass-tree. For persistent key-value stores, we use RocksDB because it's the most popular system used for these kinds of applications. Although it is important to note that mass-tree and RocksDB do not are targeting a slightly different workload. For example, we don't support range scans. Finally, we also compared with Redis. However, I won't include the numbers for Redis because Redis achieved around 1 million operations per second, maximum 1.5 million, so it wasn't really competitive. In terms of throughput, on a single thread, when the working set fits in memory, basically Faster is able to outperform all the existing systems, including the pure in-memory system. And note that this is the version of Faster that supports data larger than memory. So we were able to get pretty much the entire level of performance. And when we went to a multi-threaded setting, the performance was, the difference was much larger, and we achieved up to 160 million operations per second. And the various bars show different percentages of reads and writes, and including the first bar, which is important to us, which is a 100% read modifier write workload, which is common in streaming. In terms of scalability, when the working set again fits in memory, we noticed that Faster is almost similar to Intel TBB hash map in terms of performance on a single core. And interestingly, on 2 sockets, we were able to kind of continue to maintain the scalability across, whereas the other systems were not really able to match it. And a similar thing with blind updates was also seen, except that we kind of level off towards the end with a larger workload in this case. And the reason is that we are memory bandwidth bound because the payloads, the value sizes are 100 bytes. And with increasing memory budget, again, we wanted to show that if the data happens to fit in memory, which is the right side of the system, we actually get multiple millions of operations per second. And as expected, performance degrades with Faster when the amount of memory that is allocated is lower. And this is really because of, in the case of the write-only 100% write workload, it's because of sequential write to SSD. And in terms of the 50-50, it's because of the random reads that are happening in the workload. So to conclude, Faster is a high-performance concurrent multi-core hash key-value store that we implemented in C#, and it shows that basically we can have a single design that can have it all. So you can get larger-than-memory data support with heavy updates, exploit temporal locality, and a drifting working set, achieve essentially bare metal performance in terms of throughput when the working set happens to fit in memory, degrades gracefully when the memory is limited, and is recoverable to a consistent checkpoint after failure. And some of the ongoing works that we're doing is to integrate Faster as the state store for Trill, which is a high-performance streaming system, and as well as looking at things like scale-out and consistent recovery without blocking the system. Thank you.
So I was wondering if you achieve like 100 million operations per second, so one issue will probably be getting kind of the lookups into the system through the network. So do you have, so the numbers you measured are probably not going through the network, right?
That's right.
So do you have any ideas of how you could like use it in a like more setting where you basically have clients on a different machine, or at least in a different process?
Yeah, so we have really focused on a single node shared memory kind of system, so we did not really look at the distribution. So at least in the deployments that we are planning to use this in the first iteration, people do use partitioning across machines, so there is no cross node operations. However, you could use techniques from systems like Farm and RAM Cloud, for example, to do fast RDMA, but this is not a focus of our work.
But that will be then within the same process, the client application, or because on a single box you still won't get 1 million or 100 million network like even through a domain socket you will not get that performance. So I mean I'm just wondering.
Right. So this is on the 2-socket system, and we were getting this on 2-socket, but yeah, it doesn't scale beyond. Yeah, I think there will be other bottlenecks that we would have to deal with. Yeah.
Okay. Thanks.
So it looks like that the sort of caching behavior is really optimized around a write-only or a read-modify write-only workload, because you always are, pushing any item that you update to the tail of the log. Right. So if there's an item that just gets read a lot but never written, it'll always fall off onto disk. Right. So it seems like not quite optimized for that. Have you thought about how you might extend this to make it also act nicely with some sections of your data that are
exactly. So
update intensive?
Right. So we do cover this in the paper. So there are read hot records that we also want to be able to support. So the basic idea there is to kind of create another instance of the hybrid log that would be used only for the read operation. So it acts as a cache. And the only difference between the traditional hybrid log and the read-only hybrid log is that you wouldn't be flushing it. So you get very kind of low overhead caching mechanism for the read-only workload. So yes, we do that.
Basically a whole separate whole read-only chunk.
Yes. Yeah.
Hi, Bhajesh. You know that Anna from Berkeley is also a very high-performance key-value store. Yeah. As far as you realize, what's the common thing between your work and Anna? Common.
Yeah. So Anna is an interesting piece of work. However, it does make a lot of assumptions. So we do target full consistencies as opposed to kind of the weaker consistency of Anna. The shared memory approach allows us to get high consistency on a single machine without making that assumption. And further, the fact that things are partitioned means that handling skew is much harder in Anna compared to faster. So we can handle skew much better. And more importantly, the fact that replication is happening in Anna versus there's to handle skew, which means that it wasn't really practical for the workloads that we were looking at because it is highly memory intensive and replication would basically duplicate all the keys across basically all the cores, which would not work for us. However, they do have some follow-on work, that, as they mentioned, where they have addressed some of these problems, and we still need to learn more about that. But these are the high-level differences. The common things? Yeah. Yeah, maybe we can take that offline. Yeah.